It is a device so ubiquitous we rarely give it a second thought. Yet, the zipper is a masterpiece of mechanical engineering, a sequential locking system that relies on tolerances of less than 1/100th of an inch. Every time you pull that slider, you are engaging a series of interlocking wedges that can withstand hundreds of pounds of force. But how do we take raw spools of wire and heavy polyester thread and turn them into a mechanism that functions thousands of times without failure? Today, we go inside the factory to witness the birth of the zipper. We aren't just looking at fasteners, we are looking at the physics of the wedge and the incredible precision of high-speed die casting. At its core, the zipper is a simple machine multiplied by dozens of identical units, all working in a chain reaction of physics. If even one tooth is misaligned by the width of a human hair, the entire system fails. This is the story of how metal and fabric are forced into a perfect, permanent bond. The journey begins with the teeth, technically known as elements. Most high-durability zippers use brass, aluminum, or nickel-silver alloys. The raw material arrives as massive spools of Y-shaped wire, or in some cases, as raw ingots for die casting. For metal zippers, the wire is fed into a high-speed stamping machine. This machine is a marvel of repetitive motion, striking the metal with several tons of force hundreds of times per minute. Each strike carves out a tiny scoop on the top and a corresponding protrusion on the bottom. This is the secret to the lock. The top of the tooth has a tiny hollow, and the bottom has a tiny bump. When the zipper is closed, the bump of one tooth sits perfectly inside the hollow of the tooth above it. This mechanical interference is what prevents the zipper from pulling apart sideways. The precision required here is staggering. The metal is shaped at such high speeds that the tools must be cooled by a constant mist of lubricant to prevent thermal expansion from ruining the dimensions, because even a few microns of error would cause the zipper to jam. While the teeth provide the strength, the tape provides the foundation. This isn't just ordinary ribbon, it's a high-tensile polyester or nylon tape woven specifically to resist stretching. If the tape stretches even 1%, the spacing between the teeth would change, and the slider would no longer be able to bridge the gap. The weaving process happens on massive, high-speed looms. Thousands of individual threads are interlaced at high tension to create a fabric that is incredibly thin, yet nearly impossible to tear. A critical feature of the tape is the beading, a thickened cord along the inner edge. Think of this as the mounting rail for the teeth. In plastic or coil zippers, the teeth are actually sewn onto this bead using heavy-duty monofilament thread. For metal zippers, the teeth have two legs that will eventually be clamped around this bead. The quality of this weave determines the lifespan of the zipper. It must withstand washing machines, chemical dry cleaning, and the constant friction of the slider moving back and forth, day after day, year after year. Now comes the most critical phase of construction, the marriage of metal and fabric. The tape is fed through a precision machine while the stamped teeth are delivered via a vibrating hopper. In an instant, the machine's jaws clamp the legs of each tooth around the fabric bead. The pressure must be perfectly calibrated. Too loose, and the tooth will slide out of place. Too tight, and the metal will slice through the polyester fibers, weakening the entire structure. This process happens at a rate of nearly 4,000 teeth per minute. As the teeth are attached, sensors use lasers to measure the pitch, the exact distance between each tooth. We are talking about tolerances in the range of 0.05 millimeters. Simultaneously, the machine leaves specific gaps in the chain. These gaps mark the start and end points of individual zippers. It is a seamless flow of synchronized engineering where the physical properties of the metal are used to grip the soft, flexible tape in a permanent mechanical embrace. If the teeth are the locks, the slider is the key, but it's a key that works through geometry, not a unique pattern. The slider is usually made of die-cast zinc or plastic. Its interior is carved into a Y-shaped channel. When you pull the slider up, the wide top of the Y gathers the two separate rows of teeth and funnels them into the narrow bottom of the Y. This forces the teeth to angle toward each other and mesh. Inside most sliders is a tiny hidden mechanism, the cam lock. When the pull tab is laid flat, a small metal pin drops down between the teeth, acting as a brake. This is why your zipper doesn't fly down on its own when you're walking. The manufacturing of the slider involves injecting molten zinc into a precision mold at temperatures exceeding 700 degrees Fahrenheit. After cooling, the sliders are tumbled in a ceramic media for hours to remove any burrs or sharp edges. Every surface the tape touches must be as smooth as glass to ensure a fluid, effortless stroke. Every zipper needs a beginning and an end. For zippers that come completely apart, like the one on your jacket, we need a pin and box assembly. These components are die-cast directly onto the tape. The pin is a solid piece of metal that must slide perfectly into the box to align the 2 rows of teat for the slider. This is often where zippers fail if the alignment is off by even a fraction. At the top of the zipper, we find the top stops. These are small C-shaped metal clamps that prevent the slider from flying off the end of the tracks. They are crimped onto the tape with enough force to resist a heavy tug. Each of these components is a tiny piece of industrial hardware designed to survive hundreds of pounds of lateral tension. The box must be robust enough to handle the impact of the slider hitting it thousands of times. It is the rugged foundation that makes the entire interlocking system possible. Before a zipper leaves the factory, it must prove it can survive the real world. This is the torture test. One machine, known as the reciprocating tester, grabs the slider and pulls it up and down 500 times in a row. If the teeth snag or the tape frays, the entire batch is scrapped. But that's just the beginning. The lateral strength test uses hydraulic clamps to pull the 2 sides of the zipper apart with 50 pounds of force. This simulates the stress of a tight-fitting suitcase or a heavy coat. We also test for corrosion resistance. Zippers are placed in a salt spray chamber for 24 hours to ensure the metal won't rust or oxidize when exposed to rain or sweat. Finally, color fastness is verified. The dye in the polyester tape must not bleed, even after being soaked in a chemical bath. This rigorous, data-driven approach ensures that the tiny interlocking teeth you rely on are virtually indestructible under normal use. From raw metal wire and synthetic thread to a precision-engineered fastening system, the manufacture of a zipper is a testament to the power of mass-produced accuracy. What started as an idea by Whitcomb Judson in 1893 has been refined through a century of metallurgy and mechanical engineering. Today, we produce billions of these devices every year, each one capable of keeping out the cold, securing our belongings, and functioning with a simple flick of the wrist. It is a triumph of sequential mechanics, where dozens of independent parts work in perfect harmony to solve a simple human problem. The next time you zip up your jacket, take a second to look at those teeth. You are engaging a system built on tolerances thinner than a human hair, a microscopic wall of metal that only opens when you tell it to. It is, quite literally, engineering that holds our world together, one tooth at a time. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.